Welcome back guys, and here is my second video, digital assignment 2 for the subject computer organization and architecture. Here I have a little version, my own version of a research paper, which is design and implementation of fast floating point multiplier unit, which has been taken from the 2015 International Conference on VLSI Systems, Architecture, Technology and Applications, which is also called VLSI SATA. And here I go. So the first part of this digital assignment, or this video to be more specific, is how this paper is related to the COA curriculum, basically our subject's curriculum. This paper is related to the floating point multiplication as discussed in module 2 of our subject in our class. And a brief description of floating point numbers is that the quantities that cannot be represented by integers, either because they contain fractional values or because they lie outside the range representable within the system's bit width. Multiplication of two floating point numbers is very important for the processors. Architecture for a fast floating point multiplier yielding with the single precision IEEE standard has been used in this project. The floating point representation can preserve the resolution and accuracy compared to the fixed point. Pipeline is a technique where multiple instructions are overlapped in execution. Moving on to the second part, I have a flowchart here of the existing architecture discussed in the paper, and this has been drawn using Lucidchart because Microsoft Visio is a paid software, and obviously I couldn't get hold of it, but there's a little flowchart here of the existing architecture, and I've made it using Lucidchart. It depicts the multiplication of floating point numbers, and yeah, it's a pretty simple flowchart. I hope you will be able to understand it. And as with DA1, I'm gonna add the link to this PDF in the description down below. Please do check it out for a better understanding. And here are the tabulated results and graphs using Microsoft Office Suite, and we have synthesis report of submodules in multiplier unit using DC compiler, and then we have synthesis report of submodules in multiplier unit using Spartan, and then we have synthesis report of final multiplier using DC compiler, and then we have synthesis report of final multiplier using Spartan. Okay, I guess it's like repetition of headings but not a repetition of data, so please do check it out. And then we have diagrams of the proposed architectures discussed in the paper. These two have been made using Lucidchart. The Cogstone adder, I made it using Lucidchart, where I had to get this from the paper itself because, as you can see, it's a pretty complicated thing to make on Lucidchart, and I don't think I have access to all those features. So here's the diagram, and yeah, this is the Cogstone adder, and here's the data distribution among tree architecture, a better understanding of how it's done. Then next we have the pipelined Cogstone adder. This also has been made using Lucidchart. Then we have the fifth part of this video, which is the transistor level internal diagrams using diagramming and vector graphics application software, which is Lucidchart in my case. And yeah, here are the different blocks of parallel prefix adders connected in the way that we want the output, to configure it to give the output that we want. And the next part is the comparison of the proposed architecture with existing architecture in the reference books that we are using for the subject COA. And here are the differences, the basic differences. In the proposed architecture, denormalization is done, and so it happens too with the existing architecture in our textbooks. And in the proposed architecture, we have Cogston adder, but in the existing architecture, we don't. And then proposed architecture is faster in comparison, whereas existing architecture is slower in comparison. The proposed architecture, or PA, as I'm going to call it from now onwards, is used in DSPs, and EA, existing architecture, I'm going to call it EA from now onwards. The EA is used widely in the industry. PA has 4-stage pipelining, but EA doesn't have 4-stage pipelining. The PA does not include special exceptional values, whereas the EA does include special exceptional values. Moving on, we have the advantages of the proposed design over the existing design. I'm just going to go through it briefly because it's a lot to go through. For the duration of this video, it's going to become really long. Okay, the Cogston adder is a related prefix form of carry look-ahead adder. It creates the carry in a logarithmic order, and since logarithmic order is the fastest adder when compared to the other, and also takes extra area but has lesser fan out at each stage, which makes better performance of the adder. The order of the Cogston adder is 0 log n, is O log n actually, it's not 0, it's a typo. So yeah, the partial result obtained from the proposed multiplier will be used in the Wallace tree structure, which is 4:2 compressors. The propagation carry time is less in 4:2 compressor technique used in carry save orders. And then we have the product of mantissas is normalized and rounded off. The excess 1 is detected and the exponent is adjusted for normalization. The reduced value is finally rounded off using the rounding to nearest value to give the 23-bit mantissa of the product. A zero detect block is used in the multiplier architecture to avoid unnecessary calculations of 0 in the input. To increase the performance of the multiplier, 4-stage pipelining is used. In order to increase the performance of the multiplier, operating frequency of multiplier is increased, and then pipeline stages are inserted in the critical path. Pipelining stages reduce the latency in the output by 4 clocks. And moving on to the next part, which is the eighth part, we have the merits and demerits of the proposed and existing techniques. The existing architecture has merits like it is predominantly used by the industry, it includes special exceptional values, and it denormalizes numbers to fill the gap. And it only has one demerit, that is, it is slower in comparison. And in the proposed architecture, we have merits that list that it's fast and it can be written in Verilog HDL. It can be effectively interfaced with any DSP processor. The pipelining is the most widely used technique. And demerits, this also has just one. And it says that it does not include special exceptional values. The applications of the proposed design are as such. This is the 9th segment of this video. The proposed architecture is based on fast floating point multiplier in the IEEE 754 standard single precision format is studied. The module is written in Verilog HDL to optimize the performance architecture. The proposed design used in this project can be effectively interfaced with any DSP processor. The pipelining is the most widely used technique to get the better performance of digital circuits. Proposed the high-speed floating point multiplier is implemented with a pipeline method. The proposed design is mainly used for digital signal processors, FIR filters, microprocessors, and many more. And then the 10th and the last segment is a flowchart for the algorithm for multiplication. and here it is. I made this too on Lucidchart, and just a quick tour of the flowchart. I'll just take you through it, and there it is. Then we have the proposed multiplier unit. This flowchart has also been made on Lucidchart. Yep, a quick tour, and there you go. This brings us to the end of the presentation, and yeah, I've also attached the document of the original paper here in the end. It's a long one. Please do go through it if you're interested in the topic and you wanted a further research on it. Thank you for watching this video. Have a nice day.